Hello friends, welcome to the Core. In this video, I am going to discuss about the how to find the shear force and bending moment in a given beam. Let's go to the question. This is the question. Find the shear force and bending moment in the given beam, that is simply supported beam, and draw the shear force and bending moment diagram. First, we have to draw the free body diagram for the given beam. The beam is represented by centroidal line, longitudinal centroid line, and the supports are replaced by the reaction forces. There is a simply supported beam. In the simply supported beam, two supports to be given to a beam, and these two supports are represented by reaction forces, okay, Ra and Rb, and the applied load will be acting downward, and here it is the simply supported beam free body diagram. Let us solve the question. See, this is the free body diagram where the supports are replaced by a reaction forces and the applied load on the beam. And what to be find? We have to find the shear force, bending moment, and shear force diagram, and bending momentum diagram, as well as maximum bending in the given beam. First, to find the reactions in this given problem, we don't know the Ra and Rb. We have to find the reactions first. This is the first and foremost step we have to perform. To find the reactions, we need the equilibrium equations, where it gives the reaction forces. We can find the reactions of the beam. We can find the reactions of the beam by using the equilibrium equations. What are the equilibrium equations? Sum of horizontal forces acting right and left should be equal to 0, and sum of vertical forces acting upward and downward should be equal to 0, and sum of moments of all the forces acting in a system should be equal to 0. These are the three equilibrium equations for a member which is under equilibrium state. That means it is a determinate beam. It is not an indeterminate beam. If indeterminate beam means it's like a propped cantilever beam. It's like a propped beam. Here there is the two unknowns. Those are Ra and Rb. So we need two equations to solve this problem. That means here we need a sum of vertical forces should be equal to 0. That means upward forces should be equal to the downward forces for a equilibrium system. First we see the sum of vertical forces should be equated to the 0. I taken sign convention as upward is positive and downward is negative. So what are forces acting upward is Ra and Rb. There is no load acting upward, so these two should be equal to the force acting on the beam in the downward direction. So I written Ra plus Rb should be equal to P. P came to the left hand side, so it became minus P. So it gives Ra plus Rb should be equal to P. This is the equation number 1. And now we are going to use the second equilibrium equations, that is sum of moments in the beam at a point or at a support should be equal to 0. That means we have to take, I taken the moment about A. So if you see in the diagram, Rb into span, total span, that is length L, that should be equal to the P into half of the span, that is L by 2. Here we can see the equation P into L minus P into L by 2 equal to 0. Here I taken anti-clockwise movement as a positive and clockwise movement as negative. See here I explained how to take a moment about point A. This reaction is acting upward direction. If you see about point A, this force, this reaction gives anti-clockwise moment. So I take an anti-clockwise moment, force into perpendicular distance, and as well as clockwise moment as negative. So here P is acting downwards, it produces the clockwise moment, it is taken as a negative and equated to 0. And from this we can find the reaction RB as a P by 2, and substitute RB in the equation 1, and we will get the reaction at A as a P by 2. Simply here shortcut is, it is a symmetric loading. How to find symmetric loading? The load, external load acting on the beam is the same distance from the left hand support or right hand support. So it is called symmetric loading. In the symmetric loading, the reaction will be half of the load. So we got P by 2 and P by 2. Directly we can find by symmetric loading. Just we have to see the beam and draw the free body diagram, and then let's see how many forces are acting on the beam and find the reactions in this way. If symmetric loading, just we can observe the span, that means the load acting from the supports. Okay, now how to find the shear force? Here we can see the how to draw the shear force diagram. First at point A, that means what is the load acting on the at point A? At point A, the reaction is acting on the beam. The reaction RA value is P by 2. So we draw P by 2 as positive. I take in sign convention. At the left hand side upward is positive and right hand side downward is positive. Here I take in left hand side is positive. So at section A we got the shear force as P by 2, and there is no load acting between point A to point C. So the shear force is constant throughout the span from point A to point C. Here at point C, load is acting with a magnitude of P in the downward direction. So I taken at the section left hand side downward as negative. So let's see, I taken P as downward, that means it is a negative. Left hand side downward is negative, upward is positive. I taken here positive and left hand side downward is negative. So magnitude of P acting downwards, so it is P by 2 and minus P by 2. This vertical line should represent the magnitude of the reaction or load in the beam. Okay, here minus P by 2 is the magnitude acting on the beam due to load at point C, and from the point C to B there is no load acting in between, so the shear force is constant. And next at RB, the reaction RB is upward. I taken at section left side should be upward positive, so positive P by 2. From negative P by 2 to plus positive P by 2 will give 0. And let me explain on a piece of paper. See, at point A, shear force is upward. At the section left hand side upward is positive. So P by 2 plus P by 2 at shear force at A is P by 2, and if you see at B, at C, shear force at C is equal to plus P by 2 minus P. At the C point section, left hand side I taken downward as negative. So minus P by 2 is the shear force acting at the point C. Shear force at B. And what is the shear force at B? The reaction upward is P by 2. So here already plus P by 2 minus P plus P by 2, that should be equal to 0. Don't confuse in the drawing shear force and bending momentum diagram. Take any convention, either upward as positive or downward as positive. I taken upward shear force is positive, so at P the reaction is P by 2, so plus P by 2, and there is no load in between A and C, so it continues up to the C. Then the downward force is P, so minus P by 2 is the resultant shear force. This P by 2 in the negative sign should be continued till the B, section B, where the reaction P by 2 is acting in the positive direction, so we will get 0 at the point B. Shear force as 0 at point B, which says the shear force diagram is in equilibrium condition. In this way we have to draw the shear force diagram, and then we have to see the bending moment. Bending moment we have to find by considering either from left hand side or right hand side. We know already the bending moment at the supports in a simply supported beam is 0. That means bending moment A, bending momentum at B is 0. And for finding the bending moment at C, take either the points from A or B. I taken from point A, RA into the distance from the A to the C, that means L by 2, P by 2 into L by 2. Let's see, RA is P by 2 into L by 2, which gives PL by 4 is the magnitude acting at point B, at point C, and the moment at B, bending moment at B should be equal to the 0. Why? Because this is a determinate beam and which is in equilibrium. So if you find let us see the bending momentum at point B. RA into complete span, that means L, P by 2 into L, PL by 2 is the bending moment produced by the reaction RA at point B in the clockwise direction. So in the clockwise direction I taken bending moment as positive. So if you see here, I written PL by 2 positive, and due to the point load from the span L by 2, the load P into perpendicular distance, that is L by 2, which produces the anti-clockwise bending moment at point B from the C. That means due to point load, the bending momentum magnitude is minus PL by 2. Minus represents the bending moment in anti-clockwise due to the point load P, which is equal to the 0. So that means this is a determinate beam and in a equilibrium And if you see the maximum bending in the beam is PL by 4 is it is the magnitude of the bending moment acting in a beam at cross section C, that means at point C. If you see the how to draw the bending momentum diagram, we got bending momentum at A is 0 and C is PL by 4 and B is 0. In how to draw the bending momentum diagram, the shear force is constant. Why? Because the load is constant throughout the length, that means from the point to point it is the constant. There is no UDL or UVL. If UDL is acting, the shear force will get converted into a linear. It is load is dependent on the length of the load, run over length. The shear force depends on the run over length of the load. Here it converts into the parabola. If UDL, now here the shear force is constant and the bending momentum is one order higher than the shear force. So here the shear force is constant, the bending momentum is linear. So we can draw an inclined line, that means a slope with a constant slope. The bending momentum varies from A to C, linearly increasing. And when we can see the from point C to B, the bending momentum is linearly decreasing from point C to B. When the final beam after it looks like bending upward, that means which is called as sagging, which is called also called as positive bending. This is called as positive bending, sagging. In this video we learned how to find the shear force and bending moment, and how to draw the shear force diagram and bending moment diagram for a given beam. So I hope you understood the concept behind the shear force and bending momentum. So I end this video. Learn the thing and be creative. Thank you. Please subscribe to our channel.